how does a machine actually see? You know, it's a question that sounds like it's straight out of science fiction, but the answer, well, it comes from some surprisingly simple and really elegant math from way back. So, let's dive in and break down how a computer learns to make sense of our visual world.
When you and I look at this picture, we instantly see a car, right? Our brains just do it. We process the shape, the form, the shadows, what it's for, all of it in a split second. It's totally effortless.
But a computer, it just sees this, a giant grid of numbers. That's it. Each number is just the brightness value for a single pixel. So the big question, the really crucial question, is how on earth does a machine find a car in that sea of raw data?
Well, the first big breakthrough came when scientists realized they should stop trying to understand the whole picture at once. Instead, they figured out the secret was to simplify the image, to boil it down to its most essential part, its edges.
Just take a look at this. On the left, you've got the original photo, but on the right, it's just the outlines. The image is way, way simpler, but you can still tell it's a car instantly, can't you? This proves that almost all the important structural information is right there in the edges. And this whole process, it has a name, of course. It's called edge detection. Basically, it's a method for finding those spots in a picture where the brightness changes really sharply. And guess what? Those sharp changes almost always happen at the boundary of an object.
So why this obsession with edges? Well, for starters, it massively cuts down on the amount of data the computer has to chew through. It also keeps the all-important structure of the image while cleverly throwing out all the distracting stuff like textures and shadows. It's all about making the world simpler without losing what's important.
Okay, so we get why we look for edges. But how does a computer actually do it? How does it turn a bunch of pixels into clean, distinct lines?
Yeah, how do you translate that idea of a sharp change into code a computer can actually run with, especially when all it can see is that big old grid of numbers? The answer, believe it or not, is in a math concept called the gradient. And the easiest way to wrap your head around it is to imagine all those pixel brightness numbers as a landscape. A smooth, flat field would have a really low gradient, but a steep cliff, that's a huge, sudden change, a high gradient. An edge in an image is that cliff. Now, to measure that gradient everywhere in the picture, we use this really cool tool called a convolution kernel. You can think of it like a tiny magnifying glass, a little grid of numbers that just slides over every single pixel of the image to calculate how steep the landscape is at that exact spot.
And all of this brings us to one of the classic foundational algorithms that uses this exact technique, the Sobel operator. Now, the Sobel operator didn't just appear out of nowhere. It was a key step in this much longer journey. The first tries, like the Roberts cross operator back in '65, were pretty simple but kind of noisy. Then, in 1968, Erwin Sobel and Gary Feldman showed off their new operator at Stanford. It was a huge leap forward, and it would end up inspiring even more advanced stuff like John Caney's famous algorithm in 1986. And here's the entire toolkit for the Sobel operator. It's just these two tiny grids of numbers, these kernels. The one on the left, GX, is built to find vertical edges. See how it has negative numbers on one side and positive on the other? That mathematically highlights spots where pixels go from dark to light horizontally. The GY kernel, it does the exact same thing, but it's looking for horizontal edges. Simple as that. The whole process is super straightforward. First, you slide that GX kernel across the image, and that creates a map of all the possible vertical edges. Then you do it again with the GY kernel for the horizontal ones. Finally, for every single pixel, you combine the two results. If you get a high final number, you found a strong edge. This quote here really just nails it. The operator is just calculating the gradient at every single point. It's finding the direction of the steepest possible climb from dark to light. It's a beautiful, simple mathematical way to find the boundary of an object.
But, of course, a technique from 1968 is going to have some limitations. So where did we go from there? Well, that brings us to more advanced algorithms and eventually to modern AI. So, for all its speed and elegance, Sobel had one major weakness. It was really sensitive to noise. It would often pick up on random, grainy pixels in an image and think they were real edges. And that, as you can imagine, could really mess up any later analysis. And that weakness is what led to things like the Caney detector, which really shows you the trade-off here. Caney is way more complex, it's a multi-stage process, so it's a bit slower. But the results? They're much more accurate. It gives you these crisp, thin, one-pixel lines, whereas Sobel's edges can sometimes be a bit thick and fuzzy. And that brings us to today,
where the game has totally changed again. Modern AI models, things like convolutional neural networks, they don't just follow a fixed rule. They actually learn to find edges by looking at millions of images. They're not just detecting a change in brightness, they're learning to understand context, which lets them find meaningful edges in a way that's much, much closer to how our own brains work.
So, with all this incredible new technology, why are we even talking about a simple filter from the 1960s? Why does the Sobel operator still matter?
Because its principles are absolutely everywhere. It laid the groundwork for object recognition. It inspired generations of better and better algorithms. Even its core idea of simplifying an image is still used to make data transfers more efficient. But the most important thing? Its fundamental concept, using a little kernel to find a specific feature, is the very same principle that's at the heart of the complex AI that powers things like self-driving cars and medical imaging today.
It's just an incredible legacy, isn't it? This simple, elegant little piece of math, first shown to the world in 1968, has become a fundamental part of how we give sight to our most advanced technologies.
It kind of leaves you with a final thought, right? If some simple math was all it took to teach machines to see the outlines of our world, what are they eventually going to learn to see between the lines?